2 tiếng cho ăn lần. Thôi, Kha chở quá vậy. Chờ luôn hay là bắt đầu? 5 phút nữa nha. Okay. Bài này dễ lắm. Dễ lắm. Tại vì không làm được thì thôi. Final project. Final project của em. Final project của em. Yeah. Nhiều khi nó vậy đó. Nhiều khi nó vậy. Nó là đúng hết được. Đâu thể là đúng hết được. Tom, mấy bạn hỏi là có thể share cho mấy bạn đó cái HMD, cái bài mẫu được không? Kiểu các HMD proposal hoặc là bài Felix hoặc là bài của em, kiểu để có dàn. Tại vì Word của người ta, nếu mà không share bài Felix được, share bài của em cũng được. Share bài của em nè. Đúng rồi, anh hỏi Felix đi. Felix ok. Felix ok. Đừng xem mấy bài chân lý này nọ. Nó commercial. Chắc là bắt đầu nha. Bắt đầu nha mọi người. Okay. Hello guys. Welcome to the morning lecture. So today is not a long lecture. Today is just for me to show off my final project again. So this is my fourth time present this project. So in this morning, I'm gonna walk you guys through the notebook, and in the afternoon, first half we go into try to run the training of the model, and the second half I will let you free so you can finish your proposal for your final project, and also maybe you guys can work on a hackathon and finish it. And so let's get it started. So you know, like when I was in the design agency, you know, like our work file is like measured by gigabyte because the image quality in design is so important. You don't want to compress your photo. You want everything raw and everything like as its best quality. So we need to have like external hard drive, a lot of them to store our images and also design. So that's why when I came to the class of Mariana, I was thinking like, I want to do something with design. I have the rough idea that I want to do something with the design. And Tom has introduced me about GAN. And while researching about GAN, I found the ESRGAN, which stands for Enhanced Super Resolution Image. And its power is to make a low resolution image become a high resolution one, or in other words, like make a small image become a bigger image without decreasing the quality of the pixel. So that's the idea. And when I saw that, I was like, no way, this is magic. Like this, you know, like this is not something that common. So for this project, it's not something that I create by myself. It's an implementation from a research paper from the Chinese University of Hong Kong. And a lot of people has worked on this topic for the last decade. And by now, the ESRGAN in 2018, this is the state of the art of the enhanced super resolution images. So let's see what's going on here. So just like any other GAN model, we just use like the common generator and discriminator for the training. And to dig deep into the model, I'm gonna show you the notebook later. But firstly, let's take a look at the result. If you guys came to the demo day, you already saw this thing. So from an image of 500 and 300, we upscale into like 4 times per height and 4 times per width. So we have like about 2000 and 1500. And let's take a look of the pixel quality. This is insane. Like all the pixelate nose and eyes as we turn back into like very smooth way. And I think this is awesome to work on like a human face because this is hard for you to, it's easy for you to work on landscape, but it's hard to work on human face. So this is kind of like a good milestone. And also like you see the picture here, it's not like pixelate anymore. Like this. Can you see it? Yeah. The eyes is already restored. You can see the eyes are clearly over here. For this one, again, and this picture, I really want to show you the way they reconstruct the photo. It's so elegant and so clever. Like you can see the stripe of the surfer right here. This you barely recognize this stripe on the shoulder, but here they fully restore the stripe on the shoulder, and also like the head, him, and the hair, the waist, and on his hips is also like fully restored. So this is awesome. And the next milestone is my project I want to explore. It's like the way they reconstruct the detail, the texture. And for this image, I was successfully not only like 4 times per width and 4 times per height, but I got it like 8 times. So 8 times per width and 8 times per height. So in total, it's like 64 times bigger than the original image. As you can see, like all the edges here are fully restored into this. But there's still like a little bit like a limit here. It's like the pixel here, and when they restore to here, it's kind of like clumpy. But I think it's good for the texture images like this. And this one, I took a very super small image, only 200 and 200, and I tried to 64 times upscale it into 1000 and 2000. And my milestone for this one, I want to show you guys is that because here we barely can see the word right here, but after upscaling, you can sharpen the edge of the letter, and for some letter right here, you can fully restore it to the original shape of it. It's maybe not clear yet, but now you can read it and somehow guess what this means. So this is the output of the project. I just want to show you guys. And now let's dig into the notebook to see what's going on in the notebook that makes these things happen. Okay. Interesting? No? Okay, so I have the notebook 5 in the folder of Tonga. Let me drag this one down a little bit. So welcome to my notebook. This is the one that I submit to the Coder School for my final project. If you want to read more about it, you can read the introduction of the project to understand it more. This is the result from the research paper. Bicubic is, okay, let's first talk about the history of super resolution image, how people did it before. So at the beginning, the technology is very simple. We use nearest neighbor, bilinear or bicubic. It's just like, there's nothing smart right here. It's just like, if you see that pixel, then you want to have another pixel next to it, so just copy it, like based on the previous pixel or the neighbor of that pixel. So there's nothing smart right here. And then it's come to a very simple convolutional network, very simple. They have like 3 convolution layer right here. It's the beginning of the machine learning in super resolution. And then after that, it comes to using the ResNet. Anyone remember the ResNet? They use the residual model so that it prevents the gradient from vanishing. And so we can build the model like a lot deeper, this one. And then after that, it comes to the super resolution gain, or later in my project is the enhanced super resolution gain. So that is some technique that we have used before. And this is the kind of like comparison of each technique. You can see the bicubic, the oldest one right here. It restores the image, like it makes the image bigger, but it doesn't guarantee you the pixel quality. We come to the ResNet. It's kind of over smooth, I would say, because like every detail here is like over smooth. But when it comes to ESRGAN, the model pay more attention on the detail. Yeah, and that's what we discussed yesterday. We discussed like the art of GAN is that it has the ability to generate data, to generate the detail, to generate the texture for you. So that's why GAN is so important and so powerful. And between the classic super resolution GAN, ESRGAN, and the enhanced version of that is also see some improvement. From this, a little bit over smooth, it's come to here. So it's get more and more and more better. Okay. For this project, I have my very special thanks to some people on GitHub. We have 2 projects that about ESRGAN, but in TensorFlow 1, the code is, I would say, completely different. It's like written in different language. And I also like have a lot of inspiration from the DC gang about how a gang works. Okay, so let's first we load the libraries. Okay, it's going to be sleepy. Okay, so this is how I organize my workspace. We have the biggest folder at ESRGAN, and in the data, we have one folder for data to save all the data set. And we have one folder for log, which can you save like all the checkpoints, all the text, all the output, all the sample, everything from the training. And for this time, we use the diff2k, the diff2k dataset. Diff2k dataset is the dataset that's exclusively for the task of super resolution. The train, so the diff2k have a low resolution folder and a high resolution folder. Like two pictures are the same but different in the quality. And in the training set, we have 800 photos. In the validation test set, we have like 100 photos. It sounds very like small, but later when we apply data augmentation, it will become like huge. Okay, and I also have a sample so that we can see the changing when we training it. So here we have two small, very small sample, and when we training the data, we run the model, we keep like evaluate these two sample and like show it so we can see like is the model getting better. Okay. So this is the structure of the project. The first thing is like I really like to define all the path at the beginning so that later on you're not confused like which is which. Also like configuration for images, everything about the size and the color and channel, the training from batch size to the learning rate decay step. And last but not least, because like remember yesterday we talked about the loss function, that people keep adding new component to the loss function. So we have some hyperparameter for the loss function right here too. So let's jump into the main part of the notebook. The first thing I want to talk about is the class data loader. It's the class built to handle the work to load the data into the model. And because here is already the simplified version, for my version, I train on multiple dataset. The diff2k I also train on a Flick dataset from flick.com, and also a dataset for texture, like everything in the dataset is texture. But to simplify here, we only load the data from diff2k. So first thing I do right here is I define a function that's use globe to list out all the paths inside the directory that have the format PNG, which is our picture. And then I define a function of load path list to load all that path and organize it nicely inside HR train path and LR train path. So we're going to see this term a lot because HR stands for high resolution and LR stands for low resolution. So yeah. And then after I load the data into an array of path, now I load it into a data set. Everything right here, you should be very clear by this time because you have done it so many times before. And I also have a data set for the sample so I can load it in the model. Okay, so that's one thing I want to tell you guys right here is like, I like the way everything is nicely organized inside one class. So when it comes to deployment, you just like you just bring that class and you plug in together. Yeah. And also if you use like different data set inside this data loader, you may have like a definition of init to kind of like to give you the ability of change the function into different data set just by changing the name of data set. Yeah. But right here, just keep it simple, 2K. Okay, that's it for the data loader. Is there any question? It's very straightforward, and yeah, I only use the code that we have used before, right? Okay, let's continue into the image preprocess. So our photo in the dataset will look like this. At first, it looked like completely the same, right? But you notice the axis right here. This one is the low resolution one. The size of it is only like 350 and 500. But for the high resolution one, it's like 1,400 and 2,000. So when it comes to the model, we're gonna load like a couple of low resolution and high resolution together into the model. And what I want right here is like, I don't want the whole picture because it's too big. I want to crop. The first thing I want to do is like, I want to crop a square, a random square at the size I want. In this project, I think it is 128 by 128 for high resolution. And because we have the scale 4, we want to upscale 4 times. So the low resolution should be 100 to 28 divide for 4, which is the scale right here. Okay. So the first thing I want to do is like I want to crop a random square on the low resolution image. At the same time, I want to crop the same square on the high resolution image. So the two squares are the same but different in the quality of pixel, right? So how I do it? This is the class for image preprocess. Everything about the image preprocess stand here. And firstly, I choose a random point on the low resolution image by calling random uniform. It's returned to me a random number that locate the width and locate the height. And then for the high resolution image, because it's upscaling, so just multiple the low resolution one with the scale, which is 4. And then for the crop, I want to, do you remember the AI calculator? Where you try to place the image into the middle of the canvas, remember that? It's kind of the same thing. So I want to swap. I want to choose an area of the height and an area of the width. So after this part, on the low resolution one, I have a square on that area of image. And the same thing happened with the low resolution, the high resolution one also have a square. So let's see how it works. Here is the original image. After you run in the crop, it's going to crop out it, maybe something here, a very small piece here. They crop it equally onto image. And the next thing, there's no fancy right here. It's like random flip. I randomly flip it left and right to make more data set for my, make more data for my data set. And here we can see like one function called tf.condition. This is very simple. tf.condition, what is received. The parameter here is like the condition. So here I have a random number. Give me a random number. Give me a random number from 0 to 1. And if the random number is smaller than 0.5, then you keep the image the same. But if the random number is more than 0.5, please do augmentation on it. So it's just for random. I just want a random, flip it. And the next one, augmentation, I want to randomly rotate it. So here we rotate 90 degrees at a time. And by again, I call a random number from 0 or from 1 to 4. So 1, 2, 3, 4, because it's here, the data type is integer. So this random number will decide like how many times my photo will rotate 90 degrees. So it's completely random right here. So let's see it. After the flip, of course it's flip, right? And then it's randomly rotate the image. Okay. Is all the, like, is these three make sense to you? Okay. Okay, so the next one is very simple. We have seen it so many times before. It's the read image, just read image. And I have the option whether I will normalize it. And load image for training. You can allow this to crop or not crop, augmentation or not augmentation. And load and preprocess for test, because on the test set, we don't want to do any augmentation. We want the photo to be self. We don't, we want to crop it so that we can fit into the model, but we don't want to change like shift or like rotate or anything like that. Last but not least, loss sample. So, okay, let me run it. Okay, after this part, pass size. Okay. Size. Yeah, and then when it comes to this, you just call like data loader, and then you load data set. And it's, for me, it's very like, because I'm kind of OCD. Like I cannot stand up things like out control and not organized. So by this way, I think it's very neat to define like this. Yeah. Okay, after this part, we have a train data set, validation data set, and sample data set. Okay. Here is the sample that we're going to show our model. Sample. And one function right here, I think you have seen it in the DC gang or pick to pick, isn't it? It's like generate and save image. So what it's gonna do right here is like every certain amount of epoch, it's gonna load the sample data into the model and let the model predict on it, and it's bring out the result. And at the end, you're gonna have something like this. Let me look for it. Yeah, at the end, you can make some kind of GIF like this. Yeah. So it's show you the change after every epoch. That's what that function do. Save the image for the GIF. Okay, so let's get into the really important part. So what is the model? What is the black box that the low resolution image come in and come out at the high resolution image? So yesterday how did we do the upsample yesterday? Anyone remember? What's in the model that do the upsample part? Yeah, convolution 2D transpose, right? So there's a study on that, how you upsample the image. And let me show you this. Here. So what the convolution 2D transpose do is that they divide the stride by 2, and for the convolution 2D by saying stride 2, which means that you pat in the middle of the pixel 0, 0, 0 right here. You pat it inside it. And then by that you can do the upscaling. But while studying the super resolution image, people figure out that this 0 really slow down your computational speed, because like the kernel have to move like more steps to sweep all over the image. And the second reason is that the zero here during the back propagation is zero, it's all zero here. So it doesn't give us a lot of information during the back propagation. So in 2015, I think, sometime around that, she is a researcher. He come up with the idea of pixel shuffling. So simply, generally, what pixel shuffling do is that you have an image of high, width, and channel. High, width, and channel. And then you're gonna increase it by the channel. For example, from 3 channels right here, from 3 channels of an image, you increase it, you increase the depth of it onto 9 channels. Onto 9 channels. And then after that, you redistribute the pixel so that it creates the new image that's bigger than the original one. So that's the idea of pixel shuffling. As you can see right here, the pixel on the output has the logic. For example, like for the first 3 layers here, it's gonna, for the first 3 layers right here, it's gonna give you the top row of the output image, shuffling it. And then the second row will be followed by the next 3 layers. And the third row will follow by the last 3 layers. And it's continue and continue, like shuffling and weave it together to become a new, bigger image. So that's the idea of that. Okay, so let's take a look at the generator. I put all the generator code into the class of generator because it's big. So the first thing we want to do is that we want to do the pixel shuffling, so later we can upscale our image 2 times. For doing it, it seems hard, but TensorFlow helps us on this. TensorFlow have a function to do that called TF, depth to space. And what you have to remember here is the scale value. If you set the scale by 2, it means like you upscale 2 times per width and per height. If you upscale like 4, it's like 4 times per width or per height, using the like pixel shuffling idea that I just represent you guys. Okay, and we have an upsample component. Based on the research paper, the architect of it is like a convolution 2D, padding same, followed by a pixel shuffle, and then followed by a liquid value. And this is a module that we use to manually shuffle and upscale our image when it's passing through the model. Okay. Let's see. Okay, let's try to see what the upsample do right here. Okay, what we have right here. So let's say we pick out the convolution 2D. Set the filter to 64. Before that, we going to use this image. So for the purpose of showing you what the upscaling module gonna do, I'm gonna use this one as an example. It's LL rod. Wait. So we load it. long. Okay. We do the picture. Okay, so our picture has the shape of 32 by 3, and in order to flow it into the convolution 2D, I will do a little bit of notation. Okay, so now we have our image. So now we have our image in the shape of 1, 32, 32, and 3 with integer 32 data type, and then code A. So from an image 32 by 3, we pass in through a convolution 2D, have the kernel of 3, number filter of 64, and padding same. We have an image that have the same shape, but the channel is 64. And then from this one, we float it into a pixel shuffle. Okay. Yeah. And what happened here, after we flow it into the pixel shuffle, we got the new one with the shape of 64 and 64. It's like 2 times upscale from the input, because I defined the scale here is 2. And also what we notice right here is that the channel from 64 right here is reduced into 16 wide, because take a look into this, the input like this, and then the R square R right here is redistributed into the height and the width. So we don't have the R square R in the channel anymore. The R here is like the scale. So here the scale is 2, right? So 64 divided by square of 2 is like 64 divided by 4 is 16. That's why we have the shape of 64, 64, 16 right here. Okay, clear? Everybody good? Okay. So, okay. So this one is the module that responsible for upscaling our image. So let's take a look into the whole model. And this is really long. It's really complicated. So please like pay attention and be with me. Like it took me maybe like a day to really understand what happened in the model and how to implement it by code. So to help me, I'm going to pull up the research paper. So can you see it? Sorry, it's a little bit small, but can you see this part? Yeah. So this is the model of the super resolution gang, the classic one, it inherits the idea of ResNet by doing the skip connection to make a residual block. And for the SR gang, inside the residual block, there's just like basic convolution block. But when it comes to the enhanced super resolution gang, the first thing they're gonna do is they, inside that convolution of block, they remove all the batch normalization, like I discussed yesterday. And the second one is that they make these basic convolution of block become residual block. So you imagine like you have a really big residual block, and inside that residual block is another small residual block. Yeah, it's like inception. Big residual block, inside there's like small residual block. So let's see the code. I want to explain the code like from the top down for the big, from the big one to the small one. So what do we have here? We have 3 levels of the architect of the model. The first layer is the residual block, which is the super big one, right? The super big one is right here. The next level, we have a residual block. This is like this, right? This is this one. How can I explain it? Okay, so one block like this called residual block, or I call it RRDB. And the model will include 15 RRDB. So 15 of this one together. That's the first level. 15 of that together is the biggest one. And then the second level is like 1 RRDB, the second level. And inside 1 RRDB, there's multiple dense block. That's the third level, right? And inside that dense block, we have the smallest level, which is the convolution 2D layer, okay? So this is the RRDB block. To build a model, first thing, we go into define what is the input using the input layer. And reference to the model here, we have a convolution 2D layer at the beginning, right? So we define convolution 2D right here. And then after passing through this convolution 2D, the model will split into 2 branches. One branch will go like through this block, and one branch skip everything and go directly to the end of that RDB block, right? So in order to split the branch inside our model, we use TF identity. So TF identity is just like duplicate your input. From one input, they make 2 input like the same. So you can make 2 branches. After we make 2 branches, we let the one branch traverse through the RRDB block, which is this part, the RRDB block. This is this branch. It's gonna go through the block right here. So let's work on that branch. Okay, this is 1 RDB, right? This is 1 RDB. So because we have multiple RDB, we have 15 until like 23 RDB. So here we have a loop function. We call a loop for that. But now let's take a look at what happened inside 1 RDB. Inside 1 RDB, we have 3 dense blocks, right? 1 RDB, we have 3 dense blocks right here. We have 3 dense blocks. And the same thing happened right here. The data come in and it split into branches. That's why we call TF identity again to have 1 branch right here. And what happened right here? The branch come into the dense block and get the output, and then that output again go into another dense block and go out, and they multiply together and join two branches together. That's why we have like X branch minus X branch plus equal to the branch that traverse into the dense block. Are you clear? Like one branch go down here, another branch go to the dense block, and later join that branch. That's why we have X branch, this part, right? And then we do it 3 times because there are 3 dense blocks right here. And then at the end of it, at the end of this, after traverse to 3 dense blocks, we add the first branch, the original branch, right, to the branch that just get out the dense block. That's why we have the add here, to add the original input with the branch. And if you notice right here, while building the model, the research papers say that here you have a hyperparameter as theta, which define like how much of the information from the dense block that you want to join with the original branch. And we call it the residual scaling. And that's why we have to multiply it with the scaling before adding it. Like see, we multiply it with the scaling before adding it to the original branch. So that's the level of the RDB. Are you still with me? Is it clear? No? Okay, so later when you, I will send the research paper in the model if you want to look at it. And then what inside the dense block is more easy. Inside one block right here, this is what happened inside the block. So we have a convolution, we have a module of a convolution 2D, start with the ReLU, liquid ReLU. And the things right here is that this traverse to here, right? But also skip right here. And then together come to another convolution of block. And again, like this one come in, the first one come in, and the original one come in to the third one. It's like skip one to another, one to another, one to another, like this. And the way we do it is we use TF concat, like the way we do the skip connection in the pix-to-pix yesterday. So we concat on the first group, we concat the original data come in with the data come in from the first group, first one, this one, right? And then just so on and so on, so on. And we got the dense block. And onto the simplest level, the convolutional block, we just have a convolutional 2D and a liquid ReLU layer. Okay? Oof. Yes, it took me like a while to firstly understand what happened in the model and then implement it. And then after those like complicated residual block, it comes to the easy one. We pass it into an upsampling block, which already defined right here, the upsample. Yes, we pass it through the upsample. Because I want the photo to be 4 times bigger per dimension, so I use 2 upsample. Each of it will like scale 2 times, okay? And last but not least, we have like one convolutional 2D, followed by liquid ReLU and another convolutional 2D. So we finished the generator. Okay. Any question? Seems like I have a solo talk show right here. Okay, when you have time, like, okay. If you do the model summary for this model, It's gonna have like 12 million parameters. Yeah, it's really deep. Okay, let's get into the discriminator. The discriminator is really easy. Discriminator is super easy. Here I have it's just like a bunch of convolutional 2D blocks stacked on each other to extract the feature. And you can see at the beginning, we have a real image of 1 to 8, 1 to 8. And then we extract the feature of it step by step, step by step, step by step, then flatten it, get it through a fully connected layer. At the end, we have like one node to decide whether it's fake or not fake. The discriminator is really straightforward. And this discriminator have like 14 million parameters. Okay. Okay. So this one, I'm gonna talk about it later when it comes to the training of the game. So everyone, so the training, we jump into the training of the model. The training of the SR game is different from the training of DC game of Pixel. The training including two phases. The first one, we train the generator. We warm up the generator. Because if you don't warm it up, at that point, the discriminator may be too powerful. And no matter what the generator like giving you, the discriminator keeps saying no. And this will damage the training. Let me show you. If you don't warm up your generator, it's gonna look like this. It's like the generator is hard. They don't know like how can they do the image, and they keep like randomly shuffle the pixel. And the pre-train phase of this game give the generator a good warm up before they got into the task to compete with the discriminator. And let's see how we implement the pre-train phase. Okay. Do you want 5-minute break? Okay, let's have a break because I feel like people need it. Tom Joker.
She said
Cái này có đi xưa ngay hả? Đi xưa ngay hả? Ok.
Glory là hình phải có rõ rõ ủa là hình dấu này ok vậy từ hình low resolution không đọc thì thành hình high resolution đọc thì tức là ai cũng được bị ra màu người ta sẽ được không còn cái mặt lại qua đúng không? Maximum length